Welcome to another episode of Code for Thought. This episode takes us back to CERN, the European Nuclear Physics Research Facility, based near the beautiful Swiss city of Geneva. CERN is celebrating its 70th birthday this year, on the 29th of September 2024 to be precise. Apart from physics research, there's a lot going on at CERN, including engineering and of course software engineering. I already talked about some of it in a previous episode from earlier in 2024 when I talked to Spiridon Trikassis about his efforts to support the digital infrastructure with OpenStack and Kubernetes. So for this episode I want to touch on another important and well-used tool that was developed at CERN, the CERN Virtual Machine and Virtual Machine File System, or CERN VM and VMFS for short. I had the great pleasure of meeting with Laura Promberger, a CERN fellow, and Jakob Blomer, who is a CERN staff member, and in actual fact the author of CERN VM and VMFS. Far from being a fringe tool for a part of the particle physics community, both are used by a number of engineers and researchers well outside physics, and we touch on that in our conversation. But before I hand over to Laura and Jakob, I want to set the scene for our discussion. CERN has a number of accelerators and a large number of experiments, but the most widely known are probably the Large Hadron Collider, or LHC for short, and three major experiments that use the LHC: ATLAS, the Compact Muon Solenoid Experiment, or CMS, and the Large Hadron Collider Beauty Experiment, or LHCb. The collider, the LHC, has been shut down for maintenance in 2018, but 3.5 years later, in July 2022 to be precise, the LHC sprang back into action for a new round of data collection of what is known as Run 3. Not content with that, the next stage in the use of the facility is the so-called High Luminosity Large Hadron Collider, which CERN tries to get ready for operation in 2029, that's just over 5 years from now. You're going to hear what luminosity is in this context during the interview a bit later, if you're wondering. Going into the physics, however, of each of these would be far beyond the scope of this episode, indeed this podcast, and there are excellent summaries you can find at the website of CERN and each experiment. So you may wonder what all of that has to do with virtual machines and virtual machine file systems. Put simply, the amount of data any of these experiments or the collider itself produce is absolutely gigantic. And with upgrades of the LHC coming, this huge pile will grow even larger. As Jakob will tell us later, we're talking about exabytes, which, if you're wondering, is 1,000 petabytes or 1,000,000 terabytes, or indeed 1,000,000,000 gigabytes. In the olden days, experiments were able to collect, store and prepare the data from an experiment directly on site at CERN. But with the sheer deluge of data coming from colliders and experiments like LHC, ATLAS, CMS and LHCb, this is no longer feasible. And so different ways have to be found how to distribute the burden of handling this amount of data, as well as the software that comes with it. Which is how the journey of creating the CERN Virtual Machine and Virtual Machine File System got on its way, as you will now hear in my conversation with Laura and Jakob. Hello Laura, hello Jakob. Very nice to meet you today, and a very exciting subject, CERN VM and VMFS. But before we do that, I would like you to introduce yourself, please. Maybe we can go with you first, Laura.
Hello, my name is Laura Promberger. I'm a senior fellow working on CERN VMFS. This is the project we talk about today. And senior fellow is a form of postdoc you can do at CERN. And I'm at CERN since my master thesis, where I first joined the computing group of the LHCb experiment, where I first worked on a pilot study to port the code from x86 to ARM and PowerPC. And afterwards, I stayed on to do my computer science PhD in collaboration with the University Heidelberg in Germany, where I then worked on data compression technologies in a high throughput environment. And now since 2 years I'm with CERN VMFS.
Jakob.
Hello, I'm Jakob Blomer. I'm a staff member here at CERN in the scientific software group. I'm a computer scientist by training. I'm also the original author of CVMFS, of the CERN VM file system, which was developed in the course of my PhD thesis.
Oh, right. Okay. Is that the direct result of your PhD thesis then?
It is a main result of my PhD thesis, yes.
Let's go straight into it then. We have the virtual machine and then we have the virtual machine file system. One obviously needs the other. So let's start maybe with the virtual machine. What is it and what kind of problems were you trying to solve with the virtual machine before we go on to the file system?
Right. I roll back a little bit. In order to process the data of the LHC experiments, the high energy physics community realized that CERN alone could not do this anymore. So this was a change from previous experiments where the data processing happened next to the experiment. For the LHC experiment, the model changed. And the model changed to become a globally distributed computing batch system, if you will. This is what we called the grid. And it comprises order of magnitude 150 sites, so data centers of different sizes, all around the globe at universities and institutes around the world. So, of course, this comes with all the problems of distributed systems.
Yeah.
One of the problems is how to distribute the data, and that was addressed.
Sorry, can I just ask the amount of data? Because we're talking about LHC and experiments like Atlas, CMS, etc. The amount of data that is coming in, why is that not sufficient? How big are they? What are we talking about?
Right. So initially, this was the petabyte scale. So we were talking tens of petabytes, then hundreds of petabytes, and the actual data taking started something like 10, 15 years ago. So today, we are actually speaking about exabyte scale. So that the total volume is in the range of 1-2 exabytes. And this is going to grow. So it grows as much as it can. It's like a gas. So whatever space it can take, it will use.
Nice analogy.
Right. And one of the perhaps surprising problems that we encountered was you not only need data, but you also need the software. So all of these sites have to have access to the scientific software to process the data. And these software stacks are large. They change frequently, and one has to keep available many versions at the same time, for instance, for reproducibility reasons. So traditional way to install software is through packages, like package managers or a zip file with the binaries. And this was in fact what was used. So there were, these packages were sent around to all these grid sites. Grid sites had to install it on all the nodes. And it was quite a challenge to keep the whole sort of zoo of machines in sync. Now, this is when we realized that there may be some interesting solutions from cloud computing that could help us. So industry at the same time moved into this direction of cloud computing. And one of the key ingredients of cloud computing was virtualization, or is virtualization. And we realized, that would be very nice. So instead of preparing the software stacks for CentOS and for Ubuntu and for Debian, whatever those data centers would run, could we actually try and package it all in a virtual machine? So this is what CERN VM is, the virtual machine image. And we have one platform that can run universally on all the data centers, on all our scientific data centers. And this is when I joined the project. This was started like 2007-8. So brilliant idea. It had one small catch. Those images then would get very large because you have to have the software and all the images. And this became prohibitively expensive to distribute. And so the next idea was, okay, fine, if we cannot do it this way, then maybe we pre-install everything on a file system and distribute the software in this way. So we have all on a globally available file system, we mount a minimal image and then load the software on demand, file by file, whatever is needed from the file system. And that has a number of advantages. One is that at runtime, when a particular data processing job is executed, you usually need only a tiny fraction of all the software that is available. You can cache this, you can pre-install the software on the server side, and grid sites don't need to worry about that. And as always, there's again a problem in this. So now we realized, okay, that is maybe a good idea, but there is no file system which can do this at scale. There are in general very few global file systems. AFS is an example that still exists. But starting software from a file system is a very stressful task in general for a general purpose file system. So
Why?
this is when CVMFS
Mm.
was conceived as a purpose-built file system for this one use case. We install and run software from it. And then when you restricted ourselves to this one use case, there are actually shortcuts and tricks and mechanisms that one can use to make it efficient.
What's so difficult of mounting a global file system and running it? You talked
Right.
about challenges. Could you give us an
Yes.
idea of what these challenges are?
In general, for file systems, for distributed file systems, one of the big challenges is the metadata handling. So you have a single file system tree, and you would like to have a consistent view of this tree. So if two parties change things at the same time, somehow overall the tree should look consistent. And that is at scale is usually a big problem because there's an inherent single point where things need to synchronize. Now, what we realized for software is that you don't need an identical view at every moment in time at every computer, but you need only a consistent view. So if you install a certain software version, it should be either there or not there. But it's okay if it is not yet there on one node, but it is already there on another node. Then you start processing where it's available and you wait a little bit when it becomes available on another node. So that allowed us to decouple reading and writing. It's a publish-subscribe model. We publish software and we have subscribers that get incremental, atomic, consistent updates of the latest state, rather than real-time, consistent global file system tree, as you have it, for instance, with AFS.
I do remember some kind of cloud architecture where you have read-write to a database, say, but you have one route going to write to the database, and then you have another route, a separate one, that reads from the database. And there might be a time lag when something that gets written to a database is not yet available in the read database, if you like. They get synchronized in regular basis so that you separate what gets written to it from what is being read. Is that something similar to what you're describing?
Yes, I think that's the same key idea. So that is one of the challenges. That's the consistent view challenge. The other challenge is scale. Jobs tend to all start at the same time. So these is a batch system like model of computing. So you may have a data center with 1,000 nodes. They start a data processing job. They all need the same software libraries at the same time. If there is a single poor server providing all these libraries to all the nodes, maybe globally, that doesn't work. So the second key ingredient is multiple levels of caching. We see that there's a very big reuse in software libraries. So there's a great locality that we can exploit. So on every level, on the worker node, on the data center, and then also globally, there are caches deployed that cover the load.
Laura, let me hand over to you for a minute. Could you give us an idea and a flavor of what your work in this space involves and what you're working on there?
Yeah, so I'm working mainly on the client side because of high luminosity LHC. CVMFS expect an order of growth of magnitude for nearly all its metrics by a factor. So for this, I work really on the core features to improve the performance and the reliability. And right now I'm working on the download manager. So this is the one doing the download request from the internet to download the software if it's not already locally available. And there I'm working on parallelizing the decompression because CVMFS has this super nice feature that it does data deduplication and data compression. And with this, normal repositories, right now at CERN, we over all big repositories, we have around 650 petabytes of data, but on disk only 70 terabytes are stored. So it's nearly a factor 10 in reduction of data we are having. So if we can speed it up even more by having parallel decompression running on the client and also implementing a new compression algorithm, that would of course help us with LHC.
You mentioned luminosity. This is maybe something that listeners might not be familiar with if they're not working in high energy physics. What do you mean by that?
So I'm not a physicist, but as far as I understand, you have this particle accelerator, and you have these bunches of particles. You have to pack them in bunches so that you can do like a single event collisions. So you have space in between to measure a single collision. And the amount of collisions you're having and how many particles are in it, that's what luminosity describes. And so with high luminosity LHC, the luminosity will increase by, I don't know what the factor is, but it's a quite huge factor. And so what the detectors are measuring will be way more data. And with this, of course, you also need to be able to process this data. And for this, you need better, larger software to handle.
So your job is really to make sure that this compression can be optimized and therefore the downloads sped up.
Yeah, so right now what we have is parallel downloading via curl. But then when the curl callback comes back and says like, here we have data, right now this is all processed by the same download thread. And it would be nice that if we have multiple threads that request the downloads, if they could handle the decompression, because that's way more expensive operation than just accepting the data and copying in a buffer. Then also changing the compression algorithm. Right now we are using CLib, but the idea is to change to C standard, which is a general purpose compression algorithm provided by Facebook. This, with the same compression ratio, is around a factor 2 or 3 times faster than CLib. So there we would also get quite an improvement in.
You have quite unique demands in your computing facilities. Are you working yourself perhaps on improving compression algorithms?
Yes, this is certainly an area of interest. I mean, this is not so relevant for the CVMFS project because what CVMFS hosts, I mean, it's our software, but it's still standard software. And in that respect, characteristics are not different from other binaries and software packages. Right. But when it comes to the data, that is an area of huge interest. Of course, where it gets really interesting is when you move away from general purpose compression algorithms to compression schemes that know something about the data. So that is then what we call lossy compression.
Yeah.
For instance, if you have floating point values, you may have either float or a double, but perhaps due to the way the detector works, you already know that there's a limited precision of those measurement values. So you can think about schemes where you store data only with this limited precision.
Okay, so that's taking us slightly away from the virtual machine, but I thought it was quite interesting anyway. So what were your guiding principles in designing the virtual machine and the file system? You mentioned the environment in which it needs to run. So there is this grid of 150 centers you mentioned, and you want to minimize the amount they need to spend in terms of downloading software, hence the file system. But how do you go about designing something like this?
Maybe let's start with the virtual machines. The problem we saw was a horizontal integration of different software layers. So one group would develop base libraries, another group would develop a certain part of scientific software based on those foundational libraries. Then we may have another group developing distributed computing libraries. So you have all these different components in libraries that in the end need to work together, but may have been installed, maintained by different groups. And this can quickly become a nightmare. And so the VM idea was the vertical software integration to prepare one stack that is well tested and we know all the components work together and it would run independent of the host operating system. At the time, this was full virtualization. Nowadays, this model is well known and loved as container virtualization. For the file system, I think one of the architectural oddities maybe of high energy physics is the federated computing infrastructure. So that is really different from what industry can do with a cloud.
In what sense?
So industry has the advantage. A cloud is one provider, one data center, one environment that can then scale to very large scale. Whereas in the high energy physics community, at least, or I think in general for academic computing, we often see a federated model where we combine computing resources from different academic data centers, but technically these data centers remain their own islands.
Okay.
And for instance, it is not that easy to, let's say, go to each and every data center and install a service that opens a port to the outside world. This was one of the guiding principles to avoid that and to say, okay, look, let's use HTTP as a transport protocol because everyone can read HTTP from the internet. That should go through all the firewalls. And we do it in such a way that we have only caches, only components without logic that we need installed on the sites. Let's say without sophisticated functionality.
So cloud centers, you mentioned cloud centers and that they're not federated, which in a way is probably true, but we know that when we look at, say, one of the biggest cloud providers, whose name I'm not going to mention, but we all know who it is. But anyway, they have different data centers around the globe. They don't just have one data center. They have maybe a couple of in the UK, then there's one in Ireland, then there's a few over Europe, and then, of course, the United States and other places. Is that not some kind of federation in itself, or how does that differ from the kind of federation that you're talking about?
I think it's still a little bit different. First of all, even though there are different locations around the globe, all of these data centers run the same stack. They are clones of the same technology stack. Secondly, so even though there are different locations available, it's, I think, in many cases still not fully transparent to the users of the cloud. I mean, oftentimes you specifically select at which location you want to run your services. Whereas for a physicist user, this is not something we would necessarily want to expose. Physics users are interested to get the results back, to run the job wherever. I think here the grid middleware probably provides more, say, hides the geographic distribution better.
Okay. So far, we've been talking about physics, but the way that I've come across VMFS is actually through high-performance computing, which may be used for many different purposes and not just physics. We do have many different supercomputing centers in Europe and all over the globe. Would that be of interest to them as well? And how could CERN VM and VMFS fit into that one?
Yes, so actually there are already quite some HPC sites that are using CVMFS for their software distribution. For example, the Digital Alliance of Computing in Canada. They are distributing nearly all their software over their HPC sites. So they have a conglomerate of all their HPC sites. It's not independent sites like what we're used to in Europe or in the US. And they all distribute the software with CVMFS. There's also this EASY initiative in Europe now, which wants to provide a common software stack to all HPC sites, which also has highly optimized for specific platform, the code precompiled. So the user just said, like before on a HPC site, module load TensorFlow or so, and then automatically you get the best optimized code of the software you can choose from for your CPU platform. It does not need to be locally installed, but it gets it from the CVMFS repository, or maybe from EASY, or maybe a local repository which is installed on the HPC side. There are currently quite some efforts going on to disseminate this knowledge, and there are already like Vega and some other HPC sites that have it installed.
Did you actually expect when you created and started working on CERN VM and VMFS that it would go to that scale?
I don't think we imagined that. I remember that sometime when we had the first prototypes, we installed 1 million files on the file system. I thought, wow, that is scalable. We have built something that works very nicely. And now last time we checked, we have a few billion of files under management.
Yeah.
And it's something that is always hard to imagine upfront. It just so happens.
Okay. Laura, how are you handling all of that? You must be dealing with quite a number of different organizations and people to maintain it all.
So we have quite a close connection with Kenneth, who is one of the main maintainers of the EASY project. Otherwise, I mean, we also have some companies that use CVMFS and provides resources. There's Jump Trading, who is paying my position. They have a very large setup, maybe in some aspects even larger than what CERN is using, and very different use cases. There's a very tight collaboration to get performance improvements that they need, but which benefits the entire CVMFS community that we integrate those. So this is quite interesting, but because I'm a developer, there is not so big community I'm interacting with. This is more for the infrastructure people.
CERN VM and VMFS are on GitHub, and I think they're publicly available. It's open source, I'm guessing. How can people get involved? How is the maintenance and how is the developer contributions handled?
I think that's not so different from other open source projects at GitHub. GitHub really defined to a large extent how we all work. and,
Yes.
and so there are issues, there are pull requests and code reviews, CI system. Yeah, so I think this is relatively standard.
Okay, but when we come to pull requests and when we come to accepting pull requests, who's doing that? Is there kind of a governance model that says, okay, there are core developers that can accept it, or can anybody accept it? Can anybody contribute, or do they have to do some onboarding? How does that work?
Yeah, there's some onboarding involved. We have a core team here at CERN, maintainer, who can merge the pull requests. And since we are still a small developer team, we have 3.5, let's say, core developers, and then a handful of contributors, which we all know. There's not yet a need for a sophisticated process.
All right, so it's a relatively small community, as Laura already said, that you're not interacting with that many people, but you probably are interacting with all the different centers because they might have requests. How are you handling that? Is that overwhelming at times because you get mad scientists all over the globe complaining about, oh, this doesn't work, that doesn't work, so how is that going to pan out?
There, the interesting part is that how CVMFS is created, that it just looks like any POSIX front end. You do ls/cvmfs/ your repository name. For most users, they're not aware that this is a special type of file system they're interacting with. So what we normally get, it's from site maintainers, hey, we see on our grid site, there are a lot of failures and here's a log, please have a look at it. This happens, yes, we have quite some issues open. We try our best to find the reproducers and fix it. Normally there's some correlation when we do a new release, that some new behavior was introduced which we didn't see before. We have a lot of integration tests to prevent unpleasant behavior, but sometimes some weird combination still creates it.
We are aware of the fact that we are on the critical path of computing. And that also means that that has an impact of how aggressively or not we change things in the code.
Yeah. And you mentioned the testing bit, which can be quite a challenge in its own right. So integration testing and other forms of testing, making sure that it runs on all these different sites. I mean, how do you go about that? That must be quite a test suite.
We have more or less a test matrix starting from CentOS 7, going to Ubuntu, and we even have a macOS client. So we have a gigantic test suite. For normal PRs, we have a quick suite, which just takes around 3-4 hours to run. And before we do the next release, we have a bigger test suite that takes I think a day or so to run. And only if all the tests are green, we would release the new version.
And we have an enthusiastic community. I think that's one of the great advantages of high energy physics. These colleagues that work at the data centers all over the place, they do not only perhaps report issues, but they can also really help us fix them. They help us with the testing, they help us in debugging, and sometimes with patches.
Okay, the final question that I have is what's next? So what's next for CERN VM and CERN VMFS?
Scaling is one of the big issues. I mean, as Laura mentioned, high luminosity LHC is coming and has challenges there for everybody, also for us. So things need to get faster, consume less resources, while at the same time we need to maintain that baseline stability. I think the other big part is the container support. We realized that container deployment actually conceptually is very similar to the problems we faced 10 years ago with virtual machine deployment. And so CVMFS can have a very beneficial role when it comes to container image deployment. But to make it work really well, it needs to be well integrated with the container runtimes, such as Containerd. And that is an interesting integration task in its own.
All right. The containers like Docker.
For instance, yes.
Right. Laura, what's next for you?
Well, as I mentioned before, I'm working on those client improvements, the parallel decompression and the new compression algorithm, which this particular thing will need a lot of rethinking because we also need to support the old version, so the CLIP compression. And what we're having is we have something called a catalog, which kind of tells you where to find which files are even available. And because those data chunks are compressed, you kind of now need to also know which decompression algorithm you will need to use to successfully decompress it and so on. So there it will take a bit of thinking because also you cannot just create a new repository. I mean, we have 70 terabytes. If you want to just set up a new repository just to change the compression algorithm, everyone will say, no, sorry, not interested. So we need somewhere a form of backwards compatibility.
Okay, excellent. But that was very interesting, and I hope it gives some people some ideas. So how can people contact you in case they have questions, or who can they contact if they have questions about CERN VM and VMFS?
Yeah, GitHub is one option.
GitHub has all the links. Also, there is a forum where if you have just questions, like GitHub issues are more for bug reporting, while if you have general question, the forum would be the better option.
Or simply by email.
There's a CERN VM and CERN VMFS email address then.
Yes, also there, but they're also our email addresses.
Okay. Okay. Well, thanks very much, Laura. Thanks very much, Jakob, and all the best for the future.
Thank you.
Thank you.
I think that CERN VM and CERN VMFS are very nice examples how tools that were developed to solve a specific problem could evolve to help in very different areas of research and engineering. And in this case, CERN VM and VMFS are used by the high-performance computing community. And later this season, you'll hear more about that in particular in an episode in which I talk to Kenneth Hosty from Ghent University and his work on EASY, which got mentioned during my chat with Laura and Jakob. As usual, there are links in the episode notes that you can look up if you want to find out more, which I hope you do. And if you want to contact me, you can do this directly from the show notes as well. There is a link at the top, or you can use email or message me on Mastodon, LinkedIn, or tools like Element or Slack. And if you like what you hear, please leave a review or consider sponsoring me on Patreon. Oh, time's up. See you next time. But before I forget, this podcast is covered by the Creative Commons license. See ya.